Welcome to the deep dive. Today, we're embarking on a pretty essential journey, I think. We're plunging into the foundational concepts that underpin, well, virtually every modern software system you interact with daily.
Yeah, things like your favorite streaming service, your banking app, you name it. These applications manage just incredible amounts of information.
Exactly. And our mission today is to unpack what truly makes these powerful systems work, specifically how they achieve three key things: reliability, scalability, and maintainability.
The big three.
Right. The pioneering computer scientist Alan Kay once made this really profound observation. It really sets the stage for our discussion.
What was that?
He said, the internet was done so well that most people think of it as a natural resource like the Pacific Ocean, rather than something that was man-made. When was the last time a technology with a scale like that was so error-free?
That's good. It's fascinating because it perfectly captures our everyday experience, doesn't it?
It really does. Our digital world often feels seamless, almost like you said, a force of nature just humming along in the background.
Yeah, but behind that smooth facade lies an incredible amount of meticulous, sometimes, heroic engineering.
Absolutely. It's a testament to the unseen complexity and the diligent effort that goes into making these systems appear simple and robust.
Appear being the key word there.
Definitely. Now, when we talk about modern applications, the ones that power so much of our lives, we're typically not talking about what engineers call compute-intensive applications.
Right, where raw CPU power is the main bottleneck.
Exactly. Think about your social media feed, your online banking portal, or, that e-commerce site where you just ordered something. For these data-intensive applications, the real challenge isn't usually how fast your processor can crunch a single set of numbers.
No, the bottleneck, the real engineering hurdle, is the sheer amount of data they handle, the intricate complexity of that data, and the dizzying speed at which it's constantly changing, flowing, and being accessed.
So much going on. And these applications are built on what you could call standard building blocks, right? Foundational tools that engineers often use without maybe much conscious thought because they are such successful abstractions.
Yeah, we're talking about things like databases, obviously essential for storing data so you can get it back later.
And caches.
Caches, yeah, for remembering the results of expensive operations to dramatically speed things up. Search indexes, which power keyword searches across huge data sets. Stream processing systems for asynchronous messaging and real-time data flows. And of course, batch processing frameworks designed for crunching just immense amounts of accumulated data over time.
These are the workhorses, the things we all implicitly rely on every single day, often without even realizing they're there.
And that's exactly the point, isn't it? These tools are so fundamental, so ingrained in modern software development that we often take them for granted.
Like plumbing.
Kind of, yeah. Most engineers wouldn't dream of writing a new data storage engine from scratch when there are countless robust databases out there, open source, commercial, whatever.
Sure.
But the reality of building complex applications is rarely that simple. There's a vast array of database systems, each with different characteristics, performance profiles, consistency models.
Why so many?
Well, precisely because different applications have different, often highly demanding requirements. The real challenge, therefore, comes in knowing not just how to use these tools, but which tools and which architectural approaches are most appropriate for a given problem.
Okay.
This raises, I think, an important question. How do engineers move beyond just being users of these tools and truly become data system designers?
Right, going from user to architect.
Exactly. It's about understanding the underlying principles that make them tick, the trade-offs involved, and then skillfully applying those principles to, well, stitch disparate components together effectively.
Stitching them together. That sounds complex.
It can be. And what's also become incredibly clear in recent years is how much the traditional lines between these categories of the data tools have blurred.
How so?
Well, take Redis, for instance. It's primarily known as a versatile in-memory data store, cache.
Super fast.
Super fast. But it's also very commonly pressed into service as a message queue or a publish-subscribe broker.
Okay, doing double duty.
Right. Or consider Apache Kafka.
Hey.
It started as a distributed messaging queue, but now it offers database-like durability guarantees, sophisticated stream processing capabilities, and even serves as a durable log for things like event sourcing.
So it's not just one thing anymore.
Not at all.
Yeah.
This blurring of boundaries means that engineers are constantly picking and choosing from this diverse toolkit, stitching different general-purpose tools together using custom application code to meet the unique and specific needs of their systems. It's a creative, often complex, active synthesis.
Synthesis. That's a powerful way to frame it. And this synthesis is precisely where you get what we might call a composite data system.
Hmm.
Imagine you've got your main relational database, right? But you also need lightning fast reads, so you add a separate caching layer, maybe something like memcached.
Common pattern.
Then, for full-text search across your data, you might integrate a dedicated search server, like Elasticsearch or Apache Solr.
Another piece of the puzzle.
Exactly. In this common setup, it's typically the application code's job to keep all those different pieces, the caches, the search indexes, in sync with the main database.
Right, maybe it updates the cache when data changes or reindexes documents when they're modified. Something has to coordinate.
But here's the clever part, and it's, a testament to good design.
Yeah.
The Services API, the public interface that other clients or services interact with, it hides all those intricate implementation details.
Abstraction again.
Exactly. From the outside, it just looks like one seamless, coherent system providing specific functionalities. You've essentially created a new special-purpose data system out of smaller, general-purpose components.
And this new custom system comes with its own set of guarantees, like ensuring the cache is always correctly updated or invalidated, or that search results are always fresh.
It's this hidden layer of complexity that provides a simplified, consistent experience to the end user.
And this is precisely where the most challenging and crucial questions arise. When you're building such a composite system,
Yeah.
how do you ensure that your data remains correct and complete, even when unexpected things go wrong internally? A network glitch, a server crash, or even, a human error.
Okay, data correctness. What else?
How do you consistently provide excellent performance to your users, even when parts of your system might be degraded or under heavy load?
Performance consistency. Got it.
How do you design it so it can handle a massive increase in user load or data volume without collapsing? That's scalability.
Right.
And what does a truly effective and extensible API for this composite service look like? One that can evolve over time.
These aren't just theoretical questions, are they? They dictate the success or failure, the longevity and utility of your application in the real world.
Absolutely. While many factors influence these design decisions, the team's skills, existing legacy systems, budget, time,
Sure.
our focus today is on three critical non-functional concerns that are important in most software systems, whether it's a tiny startup prototype or a global enterprise platform.
And those are?
Reliability, scalability, and maintainability. These aren't just buzzwords you throw around in a meeting. They are the fundamental pillars that determine whether an application can truly serve its purpose and deliver value in the long run.
Okay, fundamental pillars. Let's dive right into that first one. Reliability. We all have an intuitive idea of what reliable means, right?
I think so.
For software, it generally means the application performs its expected functions, it tolerates user mistakes gracefully.
Doesn't crash and you click the wrong button.
Right. It delivers good performance under the expected load, and it prevents any unauthorized access. It's the expectation that the system will just work.
Exactly. If we bundle all those together into the idea of working correctly, then reliability at its core means continuously working correctly even when things go wrong.
Okay, even when things go wrong. That's key.
It is. And this leads us to a really crucial distinction that's fundamental to building resilient systems. Understanding the difference between a fault and a failure.
Fault versus failure, what's the difference?
A fault is when one component of the system deviates from its intended specification, like a disk crashing, a server running out of memory, or maybe a network cable being accidentally unplugged. It's an internal anomaly.
Okay, one piece messes up.
Right. A failure, however, is when the system as a whole stops providing the required service to the user. The user sees the problem.
Ah, I see. The whole thing breaks from the user's perspective.
Precisely. And it's important to understand that it's practically impossible to reduce the probability of all faults to zero. Things will always go wrong. Hardware fails, software has bugs, networks glitch.
So you can't aim for zero faults.
Not realistically. So the ultimate goal isn't to prevent every single fault, but to design systems with fault tolerance, often called resilience.
Resilience.
Yeah, so that individual component faults don't cascade into a complete system failure that impacts the user. We are, in essence, building reliable systems from inherently unreliable parts.
Building reliable systems from unreliable parts. I like that. And this is where it gets particularly interesting, because sometimes in the pursuit of building truly fault-tolerant systems, it can actually make sense to increase the rate of faults deliberately.
It sounds completely counterintuitive, doesn't it?
It really does. Why would you break things on purpose?
Well, think about it. If you randomly kill individual processes or servers without warning, you're constantly testing and exercising your system's fault tolerance mechanisms.
Ah, like a stress test.
Exactly. This active stress testing builds confidence that those mechanisms will actually work correctly when an actual unplanned fault occurs naturally.
Okay, so you practice failing.
You practice recovery, really.
Yeah.
The classic example here is Netflix's Chaos Monkey.
Right, I've heard of that. It just randomly disables parts of their production system.
Pretty much, yeah. To ensure that their streaming services can withstand unexpected outages, it's a philosophy that says, if we don't actively break things, we won't know if they're truly resilient.
Wow.
By embracing this deliberate instability, you actually make the system stronger because it forces you to design for failure from the ground up, writing better error handling and recovery paths.
Because you know they'll be tested.
Constantly. It's about making failure mundane, even boring, because your systems are designed to just shrug it off. That's the real insight. Embracing chaos to find order.
Embracing chaos to find order, that's deep.
It's a powerful strategy. But it also highlights that while fault tolerance is generally preferred for operational robustness, there are specific scenarios where fault prevention is absolutely critical.
Like what?
For example, security breaches. If an attacker compromises a system and gains unauthorized access to sensitive data, that event cannot be undone.
Right, you can't just fail over from a data leak.
Exactly. There's no cure for that once it's happened. The data is out there. So in such cases, prevention through robust security measures and strict access controls is undeniably better than any attempt at cure or tolerance.
Makes sense.
But for the more common types of operational faults we encounter, hardware glitches, network drops, building in that systemic resilience is key.
So let's dig a little deeper into the common causes of these faults. First up, the ones we often immediately think of, hardware faults.
Yep, not the physical stuff.
We're talking disk crashes, RAM faults, where maybe a single bit flips and corrupts data.
Cosmic rays.
Uh,
Or just bad luck.
Power outages, or even something as simple as someone accidentally unplugging the wrong network cable.
Happens more than you'd think. If you've ever worked in or visited a large data center, you know these things aren't hypothetical. They happen with surprising regularity when you have thousands upon thousands of machines running simultaneously.
Right, the scale makes it inevitable.
And at scale, they don't just happen, they become a statistical certainty. Consider hard disks, for example. Their mean time to failure, or MTTF, is often reported to be between 10 and 50 years for a single drive.
That sounds pretty good, 10 to 50 years.
For one drive, yeah. But if you have a large storage cluster with, say, 10,000 disks,
Uh-oh.
a quick calculation reveals you should actually expect, on average, one disk to fail every single day.
Wow, every day. The numbers really add up when you multiply those individual probabilities across an entire fleet of machines.
They do.
Traditionally, our first response to this scale of hardware failure has been to add redundancy at the component level, right?
Exactly. So you'd find disks configured in a RAID setup, redundant array of independent disks, allowing data recovery even if one disk fails.
Okay.
Servers often have dual power supplies, hot swappable CPUs, and data centers employ massive batteries and diesel generators for backup power. If one component dies, its redundant partner seamlessly steps in.
This is a well-understood and effective approach, and it can certainly keep a single powerful machine running uninterrupted for years.
For a single machine, yes. However, there's been a significant fundamental shift in infrastructure philosophy.
What's that?
As data volumes and applications computing demands have continued to skyrocket, more and more applications are now designed to use larger numbers of commodity machines.
Cheaper machines, but more of them.
Right, which proportionally increases the overall rate of hardware faults across your entire infrastructure. More machines, more chances for failure.
Makes sense.
Moreover, in modern cloud platforms like AWS or Google Cloud, it's actually quite common for individual virtual machine instances to become unavailable without warning.
Really, without warning.
Yeah. These platforms are designed to prioritize flexibility and elasticity, allowing you to scale up and down quickly over the absolute reliability of any single machine.
Ah, so they expect machines to disappear sometimes.
They do. Hence, the focus is increasingly moving toward building systems that can tolerate the loss of entire machines, even entire data centers, by relying heavily on software fault tolerance techniques.
So the software handles the machine failing, not just redundant hardware inside the machine.
Exactly. These techniques are often used in addition to, or even in preference to, traditional hardware redundancy. creating a much more robust distributed system overall.
And this paradigm shift has massive operational advantages too, I bet.
Huge! A traditional single-server system often requires planned downtime for things like operating system security patches. You have to take the whole service offline, even if it's just for a few minutes.
Annoying for users.
Very. But a system designed with software fault tolerance, one that expects individual nodes to fail, can be patched one node at a time through what we call a rolling upgrade.
Ah, update one, check it, update the next.
Exactly. This allows you to update your entire system with zero downtime for the users. It's an absolute game changer for maintaining continuous operation and rapidly deploying new features or security fixes.
Zero downtime upgrades. That's the dream.
Pretty much. Now, another significant and often more insidious class of faults comes from software errors, frequently called systematic faults.
Systematic faults. Why systematic?
Unlike hardware faults, which can often be random and independent, software bugs are often correlated across multiple nodes. Think about it. The same bug in the same piece of code running on hundreds of servers means they can all fail simultaneously under specific conditions.
Ah, so if one hits the bug, they all might hit it.
Exactly, leading to far more widespread system failures. If one machine's disk fails, it doesn't necessarily mean another will, but a subtle bug in your shared caching logic or a memory leak in your request handler.
Could bring down the whole fleet.
Precisely, at the same moment.
We've seen devastating examples of this in the real world, haven't we? Remember the infamous leap second on June 30th, 2012?
Oh yeah, that was a mess. A subtle bug in the Linux kernel caused many applications and services to hang simultaneously across the internet, affected major players from Reddit to Qantas Airlines.
Just from one extra second. Yep.
Other common examples include a runaway process consuming all shared resources, CPU, memory, disk I/O, network bandwidth on multiple machines, effectively choking the entire cluster.
The noisy neighbor problem?
Sort of, yeah. Or a dependent service slowing down, becoming unresponsive, or even worse, returning subtly corrupted data, leading to a ripple effect of errors.
Cascading failures.
And then there are those dreaded cascading failures, where a small fault in one component triggers a chain reaction that brings down the entire system, one domino after another.
Scary stuff.
The real challenge with these systematic software errors is that the bugs can lie dormant for a very long time, sometimes for years. Hiding, surviving countless tests, until a very specific and unusual set of circumstances triggers them. When they do, it's often because the software was making some kind of hidden assumption about its environment, an assumption that was true for years, but eventually, for some reason, stopped being true.
So how do you fix that?
There's no single, quick fix for systematic software faults. It requires a multi-pronged approach, a combination of careful system design that anticipates failure modes.
Thinking about what could go wrong.
Right. Thorough testing at all levels. Strong process isolation, like building your system with firewalls between components so a problem in one part doesn't spread easily.
Containing the blast radius.
Exactly. Designing processes to crash and restart cleanly and quickly without losing critical state. Continuous monitoring and analysis of system behavior in production is vital.
Watching it closely.
And even self-checking mechanisms like a message queue, constantly verifying that the number of incoming messages equals the number of outgoing messages. It's about layers of defense.
Layers of defense. Okay, now for the final and perhaps most often overlooked category of faults, human errors.
Yes, us.
This is often the most surprising one, but here's where it gets truly fascinating. Despite our best intentions, humans are inherently unreliable. We make mistakes.
Unfortunately, yes.
One often cited study of large internet services found that configuration errors made by operators were, in fact, the leading cause of outages.
Get out of here. Leading cause.
Leading cause. Compare that to hardware faults, which only played a role in about 10 to 25% of outages.
Wow. That's huge. So it wasn't the disks failing, it was someone typing the wrong command or deploying the wrong config file.
Often, yeah. It highlights that even the most meticulously engineered software can be brought down by a simple typo or a misunderstood command.
It really is a humbling realization. So the crucial question becomes, how do we build reliable systems in spite of unreliable humans?
Good question. What are the approaches?
Well, several approaches that successful systems combine. Firstly, it's about designing systems in a way that minimizes opportunities for error in the first place.
Making it hard to mess up.
Right. Well-designed abstractions, intuitive APIs, and administrative interfaces should make it easy to do the right thing and actively discourage the wrong thing.
Like guardrails.
Exactly. This is a tricky balance, though, because if interfaces are too restrictive or cumbersome, people will inevitably find workarounds, which defeats the purpose and introduces new risks.
Ah, the workaround problem.
Yeah, it's about designing for cognitive ease and preventing common pitfalls without being overly paternalistic.
Okay, so good design helps. What else?
Secondly, you need to decouple the places where people are most likely to make mistakes from the places where those mistakes can cause system failures.
How do you do that?
This means providing fully featured non-production sandbox environments where engineers and operators can experiment safely with real-ish data, simulating production conditions without affecting any real users.
Safe places to play and test.
Exactly. You also need really thorough testing at all levels, from small unit tests, verifying individual code components, to larger integration tests, ensuring different parts work together, and even manual tests for user experience.
Test, test, test.
And automated testing is particularly valuable here for covering those rare corner cases that might not arise in normal operation, or for regression testing that ensures new changes don't break old functionality.
Okay. Design, sandboxes, testing, anything else?
And crucially, systems must allow for quick and easy recovery from human errors to minimize the impact of any inevitable failure.
The undo button.
Sort of. This involves making it fast and simple to roll back configuration changes, for instance, to a previous known good state.
Okay, easy rollbacks.
It also means gradually rolling out new code to a small subset of users' first canary releases or blue-green deployments.
So you limit the blast radius if something does go wrong.
Exactly. Any unexpected bugs affect only a limited audience before they're widely deployed. Furthermore, providing tools to recompute incorrect data or resynchronize corrupted states can be a lifesaver.
Tools for fixing the data afterward.
Right. Finally, robust systems rely on detailed and clear monitoring, what we often call telemetry.
Telemetry, like rockets.
Exactly like rockets. Just like how telemetry is essential for tracking a rocket after it's left the ground and understanding any anomalies or failures. You need to see what's happening inside. Comprehensive monitoring provides early warning signals, confirms assumptions about system behavior, and offers invaluable diagnostic metrics for pinpointing and understanding issues when they do occur. It's the eyes and ears of your operational health.
Eyes and ears. Okay. So how important is reliability, really? It's easy to think of it as only critical for, high-stakes systems like nuclear power stations or air traffic control software.
Right, the life or death stuff.
But even what we consider mundane applications, your everyday mobile apps, e-commerce sites, or productivity tools,
Yeah.
they need to be highly reliable too, right?
Absolutely. Bugs in business applications can lead to significant lost productivity, legal risks if financial figures are reported incorrectly.
Big problems.
And for e-commerce sites, outages can mean huge costs in terms of lost revenue and severe damage to reputation. The cost of unreliability quickly dwarfs the cost of building reliability in the first place, often.
And beyond the direct business impact, there's also a profound responsibility to our users, isn't there?
Definitely. Consider a parent who stores all their precious pictures and videos of their children in your photo application.
Oh, man. Yeah.
What if that database was suddenly corrupted due to a software bug or a hardware glitch? Would they even know how to restore it from a backup, assuming one even exists and works?
That's terrifying. It raises an important, almost uncomfortable question. How much trust do we implicitly place in the reliability of the software we use daily?
We trust it with our memories, our finances, our communications, our very digital identities. It's a huge amount of trust.
So reliability isn't optional.
Generally not. Of course, there are situations where you might consciously choose to sacrifice some reliability to reduce development or operational costs, perhaps for a simple prototype in an unproven market.
Like a quick experiment.
Right. But this should always be a deliberate, well-understood decision, a calculated risk, not an oversight. You should be very conscious of the trade-offs you are making when you decide to cut corners on reliability.
Be intentional about it. Okay. All right, let's shift gears and talk about our second fundamental pillar, scalability. This is a term thrown around a lot in tech, almost to the point of being a buzzword.
Oh, definitely. Is it scalable?
Exactly. So let's unpack what it truly means in a practical sense.
You're right. Simply saying X is scalable is pretty meaningless on its own. It's too vague.
So what should we ask?
Instead, when we talk about scalability, we need to ask very specific, quantifiable questions. If the load on our system grows this specific way, what are our practical options for coping with that growth?
Okay, how does it grow and what can we do about it?
Exactly. And How much more computing resources, CPUs, memory, network bandwidth storage, will we need to add to the system to maintain the desired level of performance as the load increases?
So how much does it cost to keep up?
Pretty much. To have a meaningful discussion about scalability, we absolutely need to quantify both the load and the performance we expect.
Quantify load and performance. Okay. To make this idea of describing load more concrete, let's look at a classic, fascinating example, Twitter. Using data from back in November 2012.
Ah, the Twitter scaling story. A
Classic.
Yeah,
Twitter has two primary operations relevant here. Posting a tweet,
the right operation.
which averaged around 4,600 requests per second, but could peak at over 12,000 requests per second during major events, and then viewing a home timeline,
Read operation, which
what,
was,
staggering 300,000 requests per second.
whoa, huge difference between write and read volume.
Massive. The interesting thing here is that simply handling 12,000 writes per second isn't the primary scaling challenge for Twitter, it's the fan out.
Fan out, explain that.
It's the complex web where each user follows many other people and is, in turn, followed by many people. This fan-out creates unique load patterns that are really hard to manage.
Precisely. Because one action posting a tweet might need to affect thousands or even millions of other users' views.
Exactly. And there were initially two broad approaches to implementing these core operations, each with very different scaling implications.
Right, the read-heavy versus write-heavy trade-off.
The original approach, which you could call read-heavy, involved a user posting a tweet, which was a relatively simple insert into a global collection of all tweets.
Easy write.
Easy write. But when a user wanted to view their home timeline, the system would then have to look up all the people they followed, find all the tweets from each of those users, and then merge and sort them chronologically.
Hard read, like a complex database query.
Exactly. Often involving a complex relational database query, potentially spanning multiple tables, requiring significant computation at read time.
And the problem?
The problem was that as Twitter's user base exploded, the system struggled immensely to keep up with the incredibly high volume of these home timeline queries. Every user's timeline request was computationally expensive.
Yeah, 300,000 complex queries per second. That's not going to fly.
Not sustainable. So Twitter made a pivotal architectural shift to what's known as a write-heavy or pre-computed approach.
This is where the ingenuity really shines, I think.
Me too. When a user posts a tweet, the system now performs significantly more work up front.
The write gets harder.
Much harder. It immediately looks up all the people who follow that user and inserts the new tweet directly into each of their home timeline caches. You can imagine it like a dedicated pre-filled mailbox for each recipient.
Pre-calculating the timeline.
Exactly. The beauty of this approach is that reading the home timeline then becomes incredibly cheap and fast because the result has already been computed and prepared ahead of time.
So the read is super easy now. Just fetch the pre-computed list.
Right. This worked dramatically better because the average rate of published tweets, 4,600 per second, is almost 2 orders of magnitude lower than the rate of home timeline reads, 300,000 per second.
So shifting the work to the right side made sense, given that imbalance.
Exactly. By doing more work at write time, they saved a tremendous amount of work at read time, shifting the load to a less contention-prone part of the system.
But there's always a catch, isn't there?
Always a catch. The downside of this write-heavy approach is that posting a single tweet now requires a lot more work on the back end.
How much more?
On average, a tweet might be delivered to about 75 followers, which meant those 4,600 tweets per second could translate into 345,000 writes per second to those home timeline caches.
Okay, that's a lot of writes, but maybe manageable compared to the read load before.
Maybe. But this average hides a critical detail that makes scaling Twitter uniquely challenging. The number of followers per user varies wildly. It follows a power law distribution.
Ah, the celebrity problem.
Exactly. Some users, like global celebrities or major news outlets, have tens of millions of followers. This means a single tweet from such a user could result in over 30 million individual writes to home timelines.
30 million writes
Yeah.
from one tweet. Wow. Delivering that in a timely manner.
Yeah. Twitter aims for within 5 seconds for most users. Delivering that kind of fan-out in 5 seconds is an enormous, non-trivial challenge that the average fan-out number completely obscures.
That average number is misleading. It's the outliers that kill you.
Right. And the final twist to the Twitter story is that they eventually moved to a sophisticated hybrid approach.
Okay. How does the hybrid work?
For most users, they still use the write-heavy approach too, where tweets are fanned out to home timelines at the time of posting. But for that small, crucial number of users with a very large follower count, the celebrities and high-profile accounts, their tweets are actually accepted from this eager fan-out.
They get special treatment.
Kind of. Instead, their tweets are fetched separately and merged with the user's home timeline when it is read, much like in the original read-heavy approach 1.
So they combine both approaches depending on the user.
Exactly. This pragmatic hybrid strategy allows them to deliver consistently good performance across the board, balancing the load and optimizing for the most common use cases while special casing the problematic outliers.
Clever. Tailoring the approach to the specific load pattern.
So for you, the listener, the key takeaway here is that the distribution of followers per user, or the fan-out load, is a critical, often hidden load parameter for Twitter. This raises an important question for you to ponder.
What are the key load parameters for your system or for an application you rely on? What defines its specific patterns of usage and growth, and where might the hidden scaling challenges lie?
Really important to think about those specifics.
Absolutely. Once you've accurately described the load on your system, the next crucial step is to investigate what happens to performance when that load increases.
Right, load goes up, what happens?
You can analyze this in two ways. Either how performance is affected when you increase load, but keep computing resources unchanged.
Does it slow down or fall over?
Right. Or how many resources you need to add to the system to keep performance constant as load increases.
How efficiently does it scale? How much does it cost?
Exactly.
Mm-hmm.
Both of these require us to describe performance quantitatively, using precise metrics.
Okay, metrics, what kind?
For batch processing systems, like large data analytics jobs on Hadoop, we typically care about throughput, the number of records processed per second, or the total time taken for a job to complete.
How much work gets done?
Right. But for online systems like web services or APIs, what's usually more important is the service's response time.
How fast it feels to the user.
Exactly. The duration between a client sending a request and receiving a response. This directly impacts the user's perception of speed and responsiveness.
Now, a quick clarification. While often used synonymously in casual conversation, latency and response time aren't quite the same thing technically.
That's right. It's a subtle but important distinction. Latency is more about the duration a request is waiting to be handled. It's the delay inherent in the system, like network propagation delay, or maybe a queuing delay before it even gets processed.
The waiting time.
The waiting time. Response time, on the other hand, is what the client actually sees from end to end. It includes not just the time it takes to process the request on the server, but also network delays, getting there and back, any queuing delays.
The whole round trip.
The whole round trip. So response time is a broader, more user-centric metric.
Got it.
And critically, even if you make the exact same request over and over to a live system, you'll almost certainly get slightly different response times each time.
Why is that? It's the same request.
In a real-world system, response times can vary a lot. So we need to think of performance not as a single number, but as a distribution of values. Most requests might be fast, but there will always be occasional outliers, those requests that take much, much longer.
The slow ones. What causes those?
This random additional latency can be introduced by anything from a background operating system process context switch, a temporary network glitch causing packet retransmissions, a garbage collection pause in a managed runtime like Java.
Ah, GC pauses. The bane of many systems.
Can be. A page halt requiring a disk read, even subtle mechanical vibrations in the server rack can affect performance. It's a complex dance of interacting variables.
Wow, vibrations. Okay, so it's variable. You often see the average response time reported in system metrics, but you're saying that can be really misleading for user experience.
It absolutely can. The mean or average doesn't tell you how many users actually experienced a certain delay, particularly those at the frustratingly slow end. It smooths everything out, obscuring the true user experience.
How so? Give me an example.
Well, imagine 99% of your requests take 10 milliseconds, which is super fast, but 1% take a full minute.
Okay, 1 in 100 takes forever.
Right. The average response time might still look pretty good, maybe around 600 milliseconds, because the 99 fast requests pull it down. But that average completely hides the fact that 1% of your users are having a terrible experience.
Ah, I see. The average hides the pain.
Exactly. This is precisely why it's usually much, much better to use percentiles when measuring response times.
Percentiles, like in test scores.
Similar idea. If you sort all your response times from fastest to slowest, the median, or the 50th percentile, P50, is the halfway point.
Okay, middle value.
Right. If your median response time is 200 milliseconds, it means half your requests return in less than 200 meters, and half take longer. It gives you a good sense of the typical user experience, the common case.
What about the slow ones, the outliers?
To truly understand your outliers, the users who are suffering, you look at higher percentiles. The 95th, 99th, and 99.9th percentiles,
Okay.
P95, P99, P99.9, are very common metrics in production systems.
P99, P99.9.
These capture the tail latencies, the experiences of your slowest users. They tell you, for example, that 99% of requests complete within, say, 1 second, while the slowest 1% take longer than that.
So you know how bad it gets for the unlucky few.
Precisely. And this is where it gets truly impactful for business.
How so?
Amazon, for example, famously focuses intensely on the 99.9th percentile for their internal services, even though it only affects 1 in 1,000 requests.
Why focus on such a small fraction?
Because the customers who experience those slowest requests are often their most valuable ones. Those with the most data, the biggest shopping carts, who have made the most purchases, or are the most active on the platform, is absolutely critical to keep those high-value customers happy.
Ah, the slow requests might hit your best customers.
Exactly. Amazon observed empirically that a mere 100 millisecond increase in response time can reduce sales by 1%.
1%, just from 100 milliseconds.
Yep. And a 1-second slowdown can reduce customer satisfaction by a whopping 16%. That's a direct, measurable impact on the bottom line. It demonstrates that optimizing for tail latencies isn't just a technical nicety, it's a core business imperative.
Wow. Okay, percentiles matter. A lot.
They do. However, it's also important to recognize practical limits. For Amazon's purposes, optimizing beyond the 99.99th percentile, the slowest 1 in 10,000 requests, was deemed too expensive for diminishing returns.
Was
Because at those extreme tails, random events, like a single background process spiking or a brief network blip, have a much greater impact, and it becomes incredibly difficult and costly to engineer them out consistently.
diminishing returns. Got it.
This trade-off between performance optimization and engineering cost is critical in design. Percentiles are also widely used in service-level objectives, SLOs, and service-level agreements.
SLAs and SLAs. What are they?
SLOs are internal targets for how well a service should perform goals the team sets for itself. SLAs are formal contracts with external customers that define the expected performance and availability of a service.
So promises you make to customers.
Exactly. An SLA might state that a service is considered up if, for instance, it has a median response time of less than 200 milliseconds and a 99th percentile under 1 second. If these metrics aren't consistently met,
And what?
customers might even be able to demand a refund or service credits, directly impacting the business financially. So those percentile targets and SLAs have real teeth.
Okay. Now, one significant factor contributing to high percentiles, you mentioned, is often queuing delays, sometimes called head-of-line blocking.
Yes, head-of-line blocking. Imagine a server that can only process a limited number of requests in parallel, perhaps constrained by its CPU cores.
Okay.
If a few very slow requests arrive first and get stuck, tying up those processing slots.
They block the queue.
Exactly.
Hmm.
Even if subsequent requests are super fast to process individually, the client will still see a slow overall response time because their request had to wait in line behind the backlog created by the slow ones.
So a slow request can make fast requests behind it look slow.
Precisely. This highlights why it's absolutely crucial to measure response times from the client side, reflecting the actual user experience, not just what the server reports it took to process.
Measure from the user's perspective.
Always. And when you're artificially generating load to test scalability, your load generator needs to send requests independently of the response time, if it waits for each response before sending the next one.
It doesn't simulate real users piling up requests.
Right. It artificially keeps the queues shorter and gives you an unrealistically optimistic measurement of how the system handles load.
Good tip for load testing. What was the other thing? Tail latency amplification.
Ah, yes, tail latency amplification. This is critical, especially in complex backend systems, where a single user request requires multiple calls to various backend services. Microservices architectures are a prime example.
Okay, one user click triggers many internal calls.
Right. Even if you make those calls in parallel to speed things up, the end user request still has to wait for the slowest of those parallel calls to complete.
The whole thing is only as fast as its slowest part.
Exactly. It only takes one slow back-end call, among perhaps dozens, to make the entire end-user request slow.
So the probability of hitting a slow call increases.
Dramatically. Even if only a small percentage of your individual back-end calls are slow, The probability of an end-user request encountering at least one slow call increases significantly if it relies on many back-end services. This leads to a higher proportion of slow end-user requests overall than you might expect just looking at individual service percentiles.
That makes sense. The more calls you make, the higher the chance one of them is slow.
Which is why monitoring these tail percentiles is so vital. To monitor this effectively, you need to calculate response time percentiles efficiently on an ongoing basis, perhaps over rolling windows like the last 10 minutes.
How do you do that efficiently? Keeping all response times sounds memory intensive.
It is. You could theoretically keep a sorted list of all response times, but that quickly becomes infeasible at scale, consuming too much memory and CPU.
So what's the alternative?
There are specialized algorithms like forward decay, t-digest, or HDR histogram that can calculate remarkably good approximations of percentiles at minimal CPU and memory cost.
HDR histogram.
Yeah, HDR histogram developed by Giltain is particularly powerful. It allows you to capture extremely accurate percentiles, even for incredibly rare tail events, across a massive range of values. Think microseconds at hours, with almost no memory overhead compared to storing raw values. It ensures that the critical experience of your slowest users is precisely understood.
Which simpler methods might miss?
Which simpler fixed bucket histograms or just plain averages would totally miss.
Yeah.
But a crucial warning that can trip up even experienced engineers.
What's that?
Never average percentiles. It's mathematically meaningless and will give you incorrect results.
Don't average P99s.
Don't average P99s or P50s or any percentile. The correct way to aggregate response time data across multiple servers or time windows is to combine the underlying histograms or data structures, like HDR histogram, and then calculate the percentile from the combined distribution.
Combine the raw data, or histograms, then calculate. Got it.
Now that we've covered how to describe load and measure performance, we can discuss the high-level strategies for coping with increased load.
Okay, how do we actually scale?
The stark reality is that an architecture appropriate for one level of load is highly unlikely to cope with 10 times that load efficiently, or maybe even at all.
What works at 1x won't work at 10x.
Probably not. If you're working on a fast-growing service, you should expect to rethink your architecture for every order of magnitude increase in load. It's an ongoing journey, not a one-time decision.
Constant evolution.
Okay.
People often talk about two main fundamental approaches, right? Scaling up versus scaling out.
That's right. Scaling up, or vertical scaling, means moving to a more powerful, typically more expensive single machine with more CPU, RAM, and storage. Bigger box.
Bigger box. And scaling out.
Scaling out, or horizontal scaling, involves distributing the load across multiple, often smaller commodity machines. More boxes. Scaling out is also known as a shared nothing architecture because, ideally, each machine operates independently without relying on shared state with others.
Okay, bigger box versus more boxes. Which is better?
Well, while a single machine system, scaling up, is often simpler to manage initially, very intensive workloads eventually hit physical limits. You just can't buy a big enough box. So eventually you simply cannot avoid scaling out to distribute the work.
So scale out is inevitable for large systems.
Pretty much. In practice, though, good architectures usually involve a pragmatic mixture. For instance, using several fairly powerful machines can still be simpler and more cost-effective than managing a vast number of tiny virtual machines, especially when you factor in the complexity of managing distributed systems, communication, and state.
A mix might be best.
Often, yeah. And related to that is the choice between elastic and manual scaling.
Elastic versus manual.
Some systems are elastic, meaning they can automatically add or remove computing resources when they detect a load increase or decrease. Think auto-scaling groups in the cloud. This is great for unpredictable load patterns or sudden spikes, like a retail website on Black Friday.
Scales itself.
Right. Other systems are scaled manually, where a human analyzes the capacity, forecasts demand, and then makes the deliberate decision to add more machines.
Human in a loop.
Exactly. Manual scaling is often simpler to implement and can lead to fewer operational surprises as you're in direct control, but requires more monitoring and planning.
Okay. What about databases? Scaling databases sounds hard.
Historically, yes. Taking stateful data systems like databases from a single node to a distributed setup introduced immense complexity related to data consistency, coordination, and fault tolerance.
All that stuff we talked about with reliability gets harder.
Much harder in a distributed setting. For this reason, common wisdom was to keep your database on a single node for as long as possible, scaling up that single node until scaling costs or high availability requirements absolutely forced you into distribution.
Avoid distributed databases if you can.
That was the old wisdom. However, as tools and abstractions for distributed systems continue to improve things like managed cloud databases, distributed SQL databases like CockroachDB or YugaByteDB, technologies like Kubernetes making orchestration easier,
The tools are getting better.
much better.
Hmm.
So this common wisdom may well change. It's conceivable that distributed data systems will become the default in the future, even for use cases that don't handle massive volumes of data or traffic, simply because the tooling makes it easier to achieve high availability and resilience from the start.
Interesting shift. So maybe distributed becomes the norm?
Could be. But it's important to stress that there's no single magic scaling sauce.
No silver bullet.
Exactly. There isn't one generic, one-size-fits-all scalable architecture that works for every application. The specific scaling challenge could be the sheer volume of reads, or the volume of writes, or the total volume of data you need to store, the complexity of that data, the strict response time requirements, the specific access patterns.
Like our Twitter fan ad example.
Exactly like the Twitter example.
Oh.
Or, most commonly, some complex mixture of all of these and more. An architecture that scales well for a particular application is meticulously built around specific assumptions about which operations will be common and which will be rare, those key load parameters we discussed earlier.
Assumptions are key.
They are. And here's the crucial warning. If those assumptions about your load parameters or usage patterns turn out to be wrong, the engineering effort you put into scaling is at best wasted, building something you don't need, and at worst it becomes counterproductive, adding unnecessary complexity that slows you down later.
Premature optimization is the root of all evil.
Something like that, especially for scaling. For an early-stage startup or an unproven product, iterating quickly on product features, getting user feedback, and finding product-market fit is almost always far more important than prematurely optimizing for some hypothetical future load that might never materialize.
Build for what you have now, iterate fast.
Generally, yes. You might build the most scalable system in the world, but if no one uses it, it was all for naught. The good news is that even though they are specific to a particular application, scalable architectures are still typically built from general-purpose building blocks arranged in familiar, well-understood patterns.
Which is exactly what we explore in depth throughout this journey. Okay, let's move on to our final but incredibly crucial pillar, maintainability.
The long tail of software ownership.
Exactly. This is often the hidden cost of software, the one that sneaks up on you. It's a well-known fact in the industry that the majority of software cost isn't in its initial development, getting the first version out the door.
Nope, that's just the beginning.
It's overwhelmingly in its ongoing maintenance. That means fixing bugs that emerge in production, keeping systems operational through upgrades and patches, investigating failures when they inevitably happen,
Firefighting.
adapting to new platforms or operating system versions, modifying the software for new use cases, constantly repaying technical debt that accumulates.
Cleaning up old messes.
And most importantly, adding new features that keep the product relevant and growing. All that work after V1.
And unfortunately, legacy systems have a bit of a bad reputation, conjuring images of dusty, arcane code bases.
Yeah, no one wants to work on the legacy system.
Right. They're often unpleasant to work on, perhaps because they involve fixing other people's mistakes or using outdated platforms or forcing systems to do things they were never originally intended for. Every legacy system is uniquely unpleasant, which makes it hard to give general recommendations for dealing with them.
So what can we do?
However, we can, and absolutely should, design new software in a way that minimizes future pain during maintenance. We can avoid creating our own legacy systems down the line.
Design for maintainability from the start.
Exactly. To that end, we focus on 3 key design principles that contribute to overall maintainability: operability, simplicity, and evolvability.
Operability, simplicity, evolvability. Okay, let's unpack operability first. Making life easy for operations teams.
This is a critical insight, often overlooked by developers focused only on features. Because, as the saying goes, good operations can often work around the limitations of bad or incomplete software.
They can keep it running even if it's flawed.
But good software cannot run reliably with bad operations. Even with extensive automation and DevOps practices, human operations teams, or site reliability engineers, SREs, are absolutely vital for keeping a complex software system running smoothly, especially when the unexpected happens. They are the first line of defense.
So we need to make their lives easier.
We do. A truly effective operations team has numerous responsibilities that extend far beyond simply keeping the lights on. They're responsible for monitoring system health and performance, quickly restoring service when an incident occurs,
Putting out fires?
systematically tracking down root causes of problems so they don't happen again, keeping software and underlying platforms up to date with security patches and new versions, understanding the intricate interdependencies between different system components,
Knowing how everything fits together.
right? Performing proactive capacity planning, establishing good practices for deployment and configuration management, executing complex maintenance tasks like platform migrations, ensuring system security, defining predictable processes for routine tasks, and critically, preserving organizational knowledge as people come and go.
That's a lot of responsibility.
It is. Good operability essentially means making routine tasks so easy, so automated, and so transparent that the operations team can focus their efforts on those higher value, more complex problem-solving and strategic activities rather than constant firefighting.
Freeing them up from toil, how can systems themselves help with that?
Systems themselves can really aid operability through their design. This includes providing excellent visibility into the runtime behavior and internal workings of the system through robust, detailed monitoring and logging. Good telemetry.
Sing inside the box.
Exactly. It's also about offering strong support for automation and seamless integration with standard operational tools like configuration management systems, Chef, Puppet, Ansible, or incident response platforms, PagerDuty.
Plays well with others.
Right. Another key aspect is machine independence, allowing individual machines to be taken down for maintenance, upgrades, or even failure without interrupting the overall system's service. Remember, rolling upgrades.
Yeah, makes maintenance easier.
Clear, up-to-date documentation, and an easy-to-understand operational model knowing that if I execute X command, Y will happen, are absolutely essential for quick diagnosis and predictable behavior.
Good docs.
Crucial.
Always. Good default behaviors are important, reducing the need for constant tweaking, but also giving administrators the freedom to safely override those defaults when needed for specific circumstances.
Sensible defaults, but configurable.
Yep. Systems should have appropriate self-healing capabilities for common issues, but equally important is providing administrators with precise manual control over the system state when necessary, allowing human intervention for complex or novel problems.
Automation where possible, manual control when needed.
It's a balance. Ultimately, it's about exhibiting predictable behavior and minimizing surprises for the people who are responsible for keeping it running 24/7.
Minimize surprises for the ops team. Okay. Our second pillar of maintainability is simplicity, managing complexity.
The fight against the big ball of mud.
Right. Small software projects can be beautifully simple and expressive with clear logic and elegant designs. But as projects grow, especially with multiple teams and evolving requirements, they often become incredibly complex and difficult to understand.
Entropy always increases.
Seems like it. This complexity isn't just an aesthetic problem. It directly slows down everyone who works on the system, which in turn dramatically increases maintenance costs. A software project bogged down by complexity is often described, as you said, as a big ball of mud, an amorphous, tangled mess where no one truly understands how all the pieces interact.
And you can see the symptoms of this complexity everywhere.
Like what? An explosion of the system's state space, where tracking what's happening becomes impossible. Tightly coupled modules that break in unexpected ways when you change one part. Tangled dependencies that make it impossible to isolate changes.
Spaghetti code.
Pretty much. Inconsistent naming and terminology that confuses developers, performance hacks that make the code unreadable, and constant special casing to work around issues elsewhere instead of fixing the root cause.
It sounds exhausting.
It is. When complexity makes maintenance hard, development budgets get overrun and schedules slip. And it's not just about time and money. In complex software, there's a much greater risk of introducing new bugs when you make a change.
Why is that?
Because it's harder for developers to understand the system and reason about its behavior. They make hidden assumptions or overlook unintended consequences. Conversely, reducing accidental complexity dramatically improves the maintainability of software. So simplicity should be a core design goal for any system you build, right alongside its functionality.
Aim for simplicity. But isn't some complexity just unavoidable?
Yes, and it's important to distinguish between accidental complexity and inherent complexity. Inherent complexity is fundamental to the problem the software is trying to solve for its users. It cannot be removed. Think of the complex rules of tax calculation or the intricate logic of air traffic control.
The problem itself is complex.
Right. Accidental complexity, however, is not fundamental to the problem itself. Rather, It arises purely from the choices made during implementation details. This includes things like boilerplate code, overly convoluted architectural patterns, or unnecessary layers of abstraction that don't actually simplify things.
Complexity we add ourselves unnecessarily.
Exactly. The best tool we have for removing accidental complexity is abstraction.
Abstraction again. Seems like a recurring theme.
It is fundamental. A good abstraction can hide a great deal of implementation detail behind a clean, simple-to-understand facade, allowing developers to focus on the problem at hand without being overwhelmed by the underlying machinery.
Hiding the details.
Yes, and a truly good abstraction can be used for a wide range of different applications, even those not originally envisioned. This reuse isn't just more efficient, it also leads to higher quality software, as improvements and bug fixes in the abstracted component benefit every application that uses it automatically.
Like building with better Lego bricks.
Kind of. High-level programming languages, for example, are powerful abstractions that hide the complexities of machine code, CPU registers, and low-level system calls. You're still using all those underlying mechanisms when you program in Python or Java, but the abstraction saves you from having to think about them directly.
Right. SQL is another example.
SQL is another fantastic abstraction. It hides complex on-disk and in-memory data structures, the complexities of concurrent requests from other clients, and even inconsistencies after system crashes. It allows you to express what you want from the data, declaratively, not how to get it step by step.
Powerful abstractions.
The challenge, however, especially in the rapidly evolving field of distributed systems, is that while there are many good algorithms and individual components, it's much less clear how we should package them into effective, robust abstractions that genuinely help us keep the system's overall complexity at a manageable level.
Abstractions for distributed systems are harder.
They often are. Building distributed systems inherently involves managing many concurrent operations, partial failures, tricky consistency models. There's a lot of inherent complexity. So what does this all mean for us as data system designers?
Yeah, what's the takeaway?
It means we're constantly looking for ways to extract well-defined, reusable components from large, complex systems to simplify and clarify their interactions, striving to push accidental complexity down into lower layers of abstraction. It's an ongoing battle against the big ball of mud.
Fighting complexity with good abstractions. Okay. And finally, our third pillar of maintainability, evolvability.
Making change easy.
Right. It is extremely unlikely, in fact, almost guaranteed, that your system's requirements will remain unchanged forever.
Change is the only constant.
Pretty much. In reality, requirements are much more likely to be in constant flux. You learn new facts about your users or market, unanticipated use cases emerge, business priorities shift, users request brand new features.
As business changes.
New platforms replace old ones, legal regulations change, and the very growth of the system itself forces architectural changes and optimizations. A system that can't easily change is a system destined for obsolescence.
This comes to roadblock.
Exactly. This is precisely where agile working patterns and the technical tools that support them, like test-driven development, TDD, and systematic code refactoring, become so valuable.
Agile helps manage change.
They provide a framework and methodology for adapting to change at a smaller, local scale within a single application or a few source code files. They help you respond to feedback and iterate rapidly.
But our deep dive here focuses on achieving agility at the larger data system level, right? How do you make an entire distributed architecture adaptable?
Yeah, how do you refactor a whole system? For instance, if we go back to our Twitter example, how would you refactor their home timeline architecture from the original read-heavy approach 1 to the later write-heavy approach 2?
That's a massive change.
It is. That's a prime example of evolvability in action at a significant system-wide architectural scale. It's about designing your system in such a way that these fundamental shifts are possible, even if difficult, rather than being completely blocked by earlier decisions.
Designing for future unknown changes.
And it really brings the whole picture together, because evolvability is directly linked to how simple and well abstracted a system is.
Simplicity enables evolvability.
Exactly. Simple, easy-to-understand systems with clear boundaries and well-defined abstractions are almost always easier to modify and adapt than complex, tightly coupled ones. That's why we use the term evolvability. It captures that notion of agility and adaptability at the architectural data system level.
Allowing your software to grow and change as your understanding of the problem and the world around it evolves.
So, to recap our deep dive into the core principles of data-intensive applications, we've explored the three fundamental pillars that determine the long-term success of almost any software system: reliability, scalability, and maintainability.
The big three. These aren't just abstract technical specifications. They are non-functional requirements, vital for any truly useful application, sitting right alongside the functional requirements of what the system is actually supposed to do.
Reliability means building systems that continue to work correctly, delivering their promised service, even when faced with a constant barrage of faults.
Whether they're random hardware failures, systematic software bugs that lie dormant for years, or the inevitable human errors that crop up in complex operations. Keep working, despite problems.
Scalability, on the other hand, is about having robust, well-understood strategies to maintain good performance and responsiveness as the load on your system increases dramatically.
And we saw that describing load accurately, often with specific nuanced parameters like Twitter's fanout, and measuring performance not just with averages, but with the critical insights gleaned from percentiles, is absolutely crucial for understanding and effectively addressing scaling challenges. Know your load, measure your tails.
And finally, maintainability. It encompasses so much, but at its heart, it's about making life better for the engineering and operations teams who work with the system day in and day out, long after it's first deployed.
That means designing for good operability, fostering simplicity by diligently managing accidental complexity, and critically, ensuring the system is evolvable so it can easily adapt to future changes, unanticipated use cases, and new demands from the business or market. It's an investment in the future of your software.
An investment in the future. I like that.
There's no single magic bullet for making applications perfectly reliable, infinitely scalable, or effortlessly maintainable. These are ongoing challenges, and trade-offs are always involved.
No easy answers.
But, as we've discussed, there are recurring patterns and robust techniques that consistently appear across different kinds of applications and industries. In future deep dives, we'll delve into the specific design decisions, architectural patterns, and algorithms that are used to achieve these goals, especially when multiple components are working together in complex composite systems and the implications of those choices.
Looking forward to that.
So, as you go about your day, or if you're building any system today, remember this. You're not just an application developer, you're inherently a data system designer.
Everyone's a data system designer now.
Pretty much, if you're building anything substantial. How might thinking about your system through the interconnected lenses of reliability, scalability, and maintainability before you even start writing a single line of code change your entire approach to building software? It's a question worth pondering deeply.
Food for thought indeed. Thanks for joining us on this deep dive. We'll catch you next time.